So linearization, let's catch back up. Was that recording? Yeah, these must start so chaotically every time. Because half the time I forget to start it. So we're gonna write tangent lines. Here we have a point. What's the other thing we need for a tangent line? A slope. How do we do that in calculus? Derivative. Are you excited to not have to answer that question anymore? Because we're about to stop doing derivatives. It's gonna be crazy. Do you want to do derivatives backwards? Because that's what we're gonna do the rest of the year. Remember how we've been subtracting one? We're gonna add one. Exactly that. We're gonna find anti-derivatives. Yeah. I like it better. All right, let's see if you remember how to take a derivative. So I'm gonna find f prime of x. I know the derivative of 1 is 0. I'll do the hard part. What's the derivative of sine x? Wow. All right, let's see if we remember any of our trig. So we're gonna plug in to this guy. We're gonna plug in 0. What is cosine of 0? Nice, we learned some trig. Excellent. So cosine of 0 is 1. If you're wondering why, here's your unit circle. Here's the point at the angle 0. This point is 1, 0. Your x value is your cosine. So what we're going to do is write our tangent line. A reminder, we usually use this form to write it. That's our point slope form. We're going to be filling in y1, m, and x1. So I'm going to do y minus what number? 1, that's coming from the y value of our point, equals m, which is also 1, x minus 0. So I could leave the line like this. The new thing I'm going to do today is oftentimes we're going to be using this line to approximate y values. So I'm actually going to go and solve for y, meaning I'm going to get this in y equals. The right-hand side of this equation is 1 times x, so just x, and I'm going to add that minus 1 over to get y equals x plus 1. What I would like to argue is that it's much easier to plug an x into this equation than it is to plug into this equation. I'd much rather plug in an x and just add 1 to it than I would try to take the sign of that function and then add 1 to it. I don't really know how to do sine of anything but the stuff on the unit circle. So what I'm claiming is that my function f of x, the 1 plus sine of x, is about equal to this guy, but only around where I kind of centered this line, where I wrote this tangent line. So around x equals 0, it does a pretty good job. That being said, farther from 0 is not doing a good job. Let's kind of look at that graphically. So this is the 1 minute where I kind of really do want to touch on calculator stuff. So if you have a calculator, wonderful. If you need one, they're behind Herbie. I'm going to open mine. It's going to take a second. So if you need to go grab one, now's a good time. He's very tall. Probably pretty easy. Did anyone go to the basketball game last night? No. Me either, but it looked exciting. Yeah, he won at the buzzer. Go Nick Alexander. I saw the video of it, but there was a big old head block in it. So.
There's a better one.
There's a better one?
Yeah, on the school Twitter page.
Oh, good to know. All right. I haven't been on Twitter today. Oh, that's an integral. We'll learn how to do that later. All right. So what I'm going to do is I'm going to graph 2 things. They're not those 2 things. Those functions are nasty. I'm going to graph the function f of x. That's 1 plus sine of x. That was the one we were given. And I'm going to graph our tangent line. That's x plus 1. And then, yeah, this is a good window. So there's 1 plus sine of x. And there is x plus 1. Now notice, really, really close to x equals 0, or the point 0, 1, that was the one we were given. This line looks like it's doing about the same thing as the function. They're very close together, so if I plugged into one or plugged into the other, I'd have a pretty close approximation. So plugging into the red line gets me about where the blue line is. That being said, it's definitely an approximation. There is some space between those curves. As I get farther away, my approximation gets less and less accurate. So what I'm going to have you do here is kind of get a numerical sense for how accurate they are. And we're going to play with my favorite calculator button, which is trace. Yeah. Oh, sorry, you're just looking.
No,
Yeah. What's up?
So I tried graphing the 1 plus sine x, and it's giving me.
Is it really, really flat?
Yeah.
Can you go to mode and make sure you're in radians? If your graph is ever really flat and you don't think it should be, check that you're in radians. All right. So what I want you guys to do is we're going to fill in this table. You're going to do it however you would like, though trace is a great option. What I'm going to do for the 1 plus sine x part is if it wants like me to plug in negative 0.5, if you're on the 1 plus sine x and you can know you are at the top left, kind of where my cursor is, see how it's blue and it's like, we're on y1. If you want to switch that, you can just go up until it's red. So I'm going to be here and I'm going to plug in negative 0.5 and press enter. What that'll do is it'll plug in and it'll give me the y value for 1 plus sine x. It's a really cool way to plug things into functions really quickly if you don't feel like typing in the whole function. So I pressed trace and then I just made sure I was on the function that I wanted. I can switch them with the arrows by going up and down. And then I just plugged in the number I wanted to. The first number on that table is negative 0.5 and press enter. I'm just going to truncate these numbers. So on the table that I have on my paper, I'm going to write down 0.520 and I'm going to write that right here. So I want you guys to practice using that trace button to plug things in. And I'd like you to finish out this side and finish this bottom one by plugging into your x plus 1. So take a couple of seconds to practice with that calculator, practice graphing and moving around your graph, plugging in. And then we will come back together. I would love if you could do both. Arguably, the bottom one you might be able to do in your head because you're just adding 1. And that's kind of the point, is that you could do it in your head if you wanted to. While you're doing that, I will take a minute. I always forget. It's supposed to be really nice this weekend, right?
On Saturday, Sunday.
Sunday's actually pretty
What?
good.
Yeah.
Okay, so if I'm gonna go outside tomorrow.
Yeah. Yes. Tomorrow's the best day.
Is there any good hiking around here? Recommendations where I could take a dog?
I mean, you could take the pathway to DC, I guess.
Oh yeah, just the WNA. Where? Oh. Oh, rest is good too. I'm gonna have to make a list.
That's it.
My parents are in Maryland.
I can't remember. It's like you get onto the trail of Point of Rocks, right?
Oh,
I like there a lot.
nice. I feel like I should take my dog out somewhere nice.
I try to type it in, and then every time I just get like this.
That probably means our window Oh, I know why. You have a I think what happens is sometimes people turn their clock on and there's like nothing in the clock to grab. So it's like, I'm not going to beat it up. What are you trying to do? Yeah. These calculators are so much more finicky than Desmos. I'm praying for the day we get to use Desmos on the AP exam. All right, I'm going to start filling in some stuff. Hopefully you're beating me to it. So as you're finishing up your table, things I would like you to notice, or kind of questions I have for you. Do you think we did a good job? So are the approximations pretty good? Where are they better versus where are they worse? So where am I getting a closer approximation versus where am I not getting a closer approximation? maybe a more opinionated question, where would you consider it not good enough? So like maybe outside of this table, where would you be like, I'm not approximating well anymore? Yeah, so what would you consider drastically different? That's a good question. That's fair. So this is a kind of cool scenario, and actually in BC we'll get to kind of do this more. So if you like the idea of approximating, just wait for Taylor series. You get an idea of how close these approximations can get. So we're matching a point and a first derivative here. Taylor series in BC, if you're interested, starts talking about what if I match the second derivative of this function, the third derivative, the fourth derivative. And you can get really, really good approximations for not that much mathematical effort. I'm just adding one. So I was doing it in my head, but you could certainly, if you're on the calculator, if you have that graphed in Y2, if you click the up arrow, notice in the top left corner of my graph, it changed to the red graph, and you can use the same trace idea. Exactly the same. I mean, we can. It doesn't have as much physical context, which is why we don't focus on it as much because, and we'll talk a lot more about position, velocity, acceleration when we get to our integrals chapters. Third derivative, it's called jerk. So if you think of like braking in a car, that motion where you're like, ugh, that is kind of what the third derivative, that change in motion there. They also have funny names. What is it? Position, velocity, acceleration, jerk, jounce. Yeah, wait, no, is jounce also snap?
Oh, yeah.
Jounce has another name. It's snap, and then it's crackle pop, and then lock drop. It's just funny. Yeah, like pop, lock, drop. Mathematicians consider themselves funny.
Are they?
Sometimes. The prime numbers have funny names too. So there's like twin primes that are 2 apart, and then there's cousin primes, and there's sexy primes.
Whoa.
They're 6 apart. Sexy primes. Those are 6 apart, right? I think they are. What?
You're not serious.
I am definitely serious.
No.
I would, let me Google it on my phone before I Google it while I'm
Yeah, don't go to images.
The school blocked
The
it?
school blocked most of them. There are some that will bypass it.
Yeah, there are primes that differ by 6. Let me see if teacher access will let me Google sexy prime.
Good luck.
Wait, so it's like actually a thing?
Yeah. I would never lie to you guys.
No.
All right, so
You're starting to think like
the school is interfering with our knowledge. Why does it let my phone search for it though?
Because
It's not blocked.
But I'm on the LCPS open.
yeah, but this computer is
They're like
from the
Ooh.
yeah, the computer's from the school.
Well, I can demonstrate. They're prime numbers that differ from each other by 6. So a good example would be 7 and 13.
5 and 11.
Oh, that makes more sense. Okay, so the Latin word for 6 is sex. That's why.
Yeah.
That makes
You guys didn't trust me. All right, back on task. Okay, so would you agree with me that we're doing a really good job approximating close to 1, but the farther we get away, the worse our approximation is? Would you also agree with me that it's much easier to plug into x plus 1 than 1 plus sine x? All right, so that's the entire idea of today. So what I'm going to show you next are the way the AP will ask you questions about this, because this provides a really good opportunity for me to give you very small pieces of information, which is what the AP test is all about. How little information can I give you to be able to make you to do a question? And then on the back page, I'm going to show you a cool party trick. So here is one of my favorite versions of this question from the AP test, because you kind of just got to trust yourself. There's some cool words in here, and it's a really easy question if you can translate what you're supposed to do. Wow. So we've got a function f. It's twice differentiable. One thing to note, we are not given a function to work with. So they're going to give me very small pieces of information to be able to do this question. They tell me f of 3 is 2, f prime of 3 is 5, and f double prime of 3 is -1. So I've got 3 very specific pieces. I want to know the approximation of f of 4 using the line tangent to the graph at x equals 3. So notice those words that we were talking about before. We're talking about approximating with a tangent line. Now, I kind of like these words better because they give you a little bit more of a clue of what to do. We want to start by writing a tangent line. So what 2 things do we need to write a tangent line? A slope. Do we have a slope? Which number on here is slope? F prime of 3. So this 5 is my slope. What else do we need? An x and a y. Where are those? All right, x is 3, y is 2. All right, anyone brave enough to do my tangent line? I'm going to start you off y minus. Perfect. So what this question is claiming, that you don't necessarily have to do it kind of right here, is it's claiming that my f of x function is about equal to if I added this 2 over to the other side. So I can't see f of x, so I couldn't graph it here. But what it's claiming is these 2 guys are doing about the same thing around what x value? X equals 3. So around x equals 3, these guys are really close together. Notice the number they're having us plug in. What number are we going to plug in? What are we trying to approximate? F of 4. So they're going to have me plug in x equals 4. That's pretty close to 3. It's all relative, so we don't know what this function is doing. It might be providing a good approximation, it might be not, but that's relatively close to 3. Goodness gracious, that is the loudest service in the entire world. That's fair. That bathroom has been open for a long time. I'm so proud. So proud of the student body. All right, so y minus 2 equals 5. What do you guys think I'm going to put in for x? 4. 4 minus 3. All right, notice y is the only thing left over. Let's solve for it. So let's go ahead and I'm going to add the 2 over. That's 5 times 1. So y equals 7 is my approximation that I'm getting. So what we're kind of concluding is that this is about equal to f of 4. Now, I don't have a picture of f of 4, so I don't quite know how close, but our approximation, we're about that. So, not a super hard question. Yeah, I like this as well. It's super easy, a lot of good knowledge, but I like that there's like only a few pieces of information, very AP style. All right, let's do another one, make it a little bit harder. One thing you'll note is that most of these questions are going to be non-calculator questions, or they're going to craft a way where a calculator like wouldn't really be helpful. So this could be on the calculator section, but there's no way that's going to help you at all. All right, I love this next question because it brings back some good verbiage from like Algebra 1. So we've got a tangent line from above. So I'm going to copy down the tangent line that we did. So it's using the same one, y minus 2 equals 5, x minus 3. It's going to be used to find an approximation to a 0 of f. All right, my computer is dying, so I'm going to grab my charger. While I do that, I need you to talk about what is a 0 of the graph? So if you had to give me like a name, if I were looking at a graph, which one? Which intercept? All right, Daniel has provided the important information that a 0 is one of the intercepts. Is that which one? Which intercept? It's an x-intercept. All right. Now, what do you guys know about x-intercepts? Specifically the points of them. What one equals 0? Y equals 0. So it's a number and 0. So what we're gonna do, yeah. Make sure you flush the toilet real loud. I want to hear it behind the door here. Yeah, like 3 times in a row. Cool. All right, what do you think I'm going to do with that y equals 0? Plug it in. All right. Notice that there we now just have an x left over. Let's solve for it. I want everyone to solve for it, and I don't want you to use a calculator. And we'll see. Consider this spicy mid notes number talk. We'll see how we can get it.
Is it by chance?
Don't tell it. Don't spoil it. Yeah. Sorry, got an email about outreach. Oh, nice. That's nice. Did anyone divide by 5 first? Is Wayne cheating? You did? It's kind of a fancy way to do it. Anyone know the answer? All right, cool. Should we make this a tiny bit harder?
No.
No, I expected that answer. I was mostly wondering, why did I ask that question? So let's make it one little step harder. We'll take a break and then I'll show you my party trick that has to go with this. So the only way I make this harder really is to just make the slope harder to find so I can make the derivative a little bit more confusing. So notice this function has a little bit of a crazier derivative. So you can imagine on your assessment that's coming up, I could maybe make you take a derivative of something that had like arctangent in it. That'd be fun and cool. What do you guys want to tell me anything about this derivative here in particular? Okay, cool. So I like that Daniel is thinking we could probably rewrite this as something to the 1/2 power. That would be helpful for taking the derivative. So I know I'm going to have 1/2 this guy to the negative 1/2. Anything else you guys want to tell me? Because chain rule, good. I have an inside function here. So what should I multiply by? Excellent. Man, I'm a little sad that we're going to stop doing derivatives. You guys are getting really good at them.
No,
Okay. Wait until we do the new stuff to say that. All right. So I'm going to re-simplify this so that I can plug a number in. So how I'm going to simplify that is I'm going to take that negative exponent. Hey. Oh, yeah. Perfect. Why don't you guys re-simplify that and try to plug in an x value to be able to find it. Remind me your last name. Perfect. Are you Dean's older sister? Are you related to Dean?
Yes, he's my brother.
I taught him algebra 1.
Oh, really?
Yeah. He's the best. All right. You just have a cookie. You have a
I'm really not sure. I told that it was one of those.
You guys know what x value to plug in? Is it what? You can be a little bit braver.
0.
0. Great.
That's what I said. Yeah.
Yeah, I was just stopping you. Whatever organized me.
Who organized?
Not me, actually.
Why would they do that?
I don't know. It's the last dog hit that I didn't know it. Yep.
Thank you so much.
Of
Sorry
course.
for interrupting.
No, you're okay.
Those later.
Do you guys get a number? All right, I was gonna keep the 2 down here. I'm gonna move that stuff to the 1/2 to the bottom. I'm also gonna take advantage of 1/2 meaning square root. So I'm gonna throw that as a square root on the bottom of my fraction. So square root 4 plus sine x.
Zero.
Yeah, because of the negative exponent. No, because I have to plug in 0 now. All right. So on the top, cosine of 0 is what number? 1. On the bottom, I have 2 square root of 4 plus, and Daniel's right, sine of 0 is 0, but I'm going to do that once I'm plugging in the 0. So this whole slope should be 1 over 2 times 2 is 4. All right. Do I have stuff to write a tangent line yet? Yeah. How do we get what on top? Cosine? So I pulled this guy. He doesn't have a negative exponent, so he should just stay at the top of the fraction. You could think of it as like times cosine x over 1 if you wanted to. So I plugged in 0, so cosine of 0 is 1, sine of 0 is 0. Absolutely. All right, so I would love to write a tangent line because I haven't done that yet, and it said the tangent line in the question. So I'm going to do y minus, what's my y value? Oh, okay. So I need to plug in 0 to that. So I could get y of 0 is our square root of 4 plus what is sine 0? 0. Cool. It is. All right. So y minus 2, not the color. Yeah, sorry, I'm trying to color code and it's not letting me. What is happening here? My computer is dying. Which one? Y minus, I was going to start my tangent line, 2 equals, what am I doing next? 1/4 x minus 0. All right, all of my answer choices are numbers. So what do I need to do? We need to solve for something, but we probably need to plug in something. Anyone see a number in our question we haven't used yet? 0.12. Now, a popular thing is to try to use that growth number, in this case 0.12, to write my tangent line. Notice they told me to write my tangent line at x equals 0. So this 0.12 is just going to get used at the very, very end. I'm going to plug in 0.12 here.